Hello, welcome you all. This is Dr. Sunil Mahagaonkar, Faculty of Mechanical Engineering Department, Government Polytechnic, Mumbai. So, in the last session, we had discussed the design of sleeve or muff coupling. So, this coupling comes under a type of rigid coupling. So, now today also, we are going to one more rigid coupling. So, that is known as flange coupling, or sometimes it is also called as protected type flange coupling. So there are two types of couplings you are going to get. One is a simple flange coupling. We do not have any protection for the bolts and nuts or the persons who are working here. So if your protected protrusion part is there in the flanges, so in that case it is called a protected type flange coupling. So this is a type of a rigid coupling. So as I said, rigid couplings, these couplings are used for very low RPM and having higher torque. Okay, as the torque is inversely proportional to the RPM. So the low RPM, why we are setting it? Because see the alignment, if you see some proper alignment is there between the shaft. So in that case only we can use the rigid coupling. So whenever we are using the rigid coupling, we are checking it whether the alignment is proper or not. That means the axis of the two connecting shaft. So they must come with along in a line. So if there is an offset is there or misalignment is there, so in that case we have to go for the flexible coupling, right? So now we will go for the presentation of flange coupling, or can say the protected type flange coupling. So the learning outcomes in these sessions are, first of all, we will go for what do you mean by rigid coupling and what are the types of that and applications of the rigid coupling, materials used for the rigid coupling, and then design of a rigid flange coupling. So the figure which I have shown you here, just we will go for the thing that you can just I will show it here. So this is protected type flange coupling is there. Okay. See here you can see these are it connects two shafts. So one shaft is here. This is one. This is the second shaft. Okay. And this shaft has got the keyway. If you see the keyway, it is at the top here. You can see it. Okay. This is the keyway. And this is at an angle of 90 degree. So if the keyway is on one shaft, it is here. The keyway in the other shaft, it will be at an angle of 90 degree. So they have provided at a difference of 90 degree because there are two reasons. One reason is that sometimes because of the vibration and all, in that key it may pass to this key and this key. That will one key of one shaft, it may comes into the grooves of the other. The other one is if you provide at an angle of 90 degree. So the strength, whatever the keyways, actually if you provide a keyway in the shaft, so that results what? There is a weakness in the strength you will get. That means it leads to the stress concentration, right? So that is what I'm saying. If you provide some recess for the insertion of a key, this is a key. So there you are going to get the stress concentration it will be reduced. So in order to this one, suppose if the length is increases, if it is connected in that, so the slot will be more. So that's why here, if I take at an angle of 90 degree, so in that case, we can say that the transmission of the torque, it transfer from this shaft to the key, and then key to the, again it comes to this left side flange, and then through the boards it goes to the right side flange, and then again through the key it goes to this one, right? If the key is in the same line, so that will cause the weakness in the strength, it will reduce it. So in order to increase the in order to get this one, that is the, in order to whatever the stress concentration, in order to reduce that one, or to increase the strength because of its keyways, so we have to take a shift of 90 degrees. Okay, so this is the flanges. Okay, and here the protection it is there. So this protection, it is given for this flange. You can see here there is a protection, and this thickness is around 6 millimeter to 12 millimeter thickness. So this, it is given, this is for just to, because when it is rotating with some speed, so always because of the vibration the nut may come out from the bolt, and when it comes out from the bolt, and if it is running, so it may hit the person who is working nearby this coupling. So in order to protect that person, as well as protect the bolt and nut from the rain, so they have made a protection cover for that. So that is called a protected type of flange coupling. Okay, if you not provided this protection, if you not provide this type of protection over here, so in that case it is simply you can call it as a rigid coupling. Okay, so the holes which you are providing in the left side as well as in the right side, they are called reamed and grooved holes. Reamed and grooved holes. So the why we are going is, the reaming is a process, right? After drilling, you are going for boring, broaching, and then reaming, so that you will get a fine finish. So to get a fine finish, so because we are inserting the bolt, right? The shank portion of the bolt, it comes in contact with the reamed and grooved holes. So if there is a clearance, so then it will not transfer the 100% torque. So reamed and grooved holes are called as a finger tight holes. It is also called as finger tight. That means there is no clearance between the bolt and the hole of this. Okay. So if it is a finger tight and a reamed and grooved holes, so then you can take the number of bolts is equal to n. Whatever the number you are considering 4, you have to consider 4 in the equation. If a clearance is there, if there is a clearance is provided between the hole of the flange and the bolt, there is a clearance, so then we can take n is equal to the effective number, n is half of the given number. If n is the total number is 6, so in that case, if the clearance is there, in that case we have to design taking n is equal to half of that, that means 3. If it is totally reamed and grooved holes, and if it is finger tight, right, no clearance, so in that case we can go for number of bolts is equal to the given number of bolts. So this is the thing when you apply it, when we are considering the number of bolts, right? So this is a protected type flange coupling. And in case of unprotected type means you will get simply the two flanges will be there. This is the flange, the hub portion, and here this is the flange. You are going to get it, right? This is the shaft. It has got a key, and this is the provision for the holes. So no protection cover for here. So this is the left side flange, and similarly we will get the right side flange. So this thing I have already, I can show it in the other figure which I drawn it here. So here you can see it. This is the left side flange. Okay. So this is a left side flange, and here is a right side flange, and this is the shaft of one. This is the other shaft. This is the key. As I said, they are at an angle of 90 degree, and why the keys are at an angle of 90 degree? In order to accommodate the weakness in the strength will be there because of the recess, the keyways are there. So in order to strengthen that one, so we are taking at an angle of 90 degrees. Okay, and these bolts are having actually threaded portion will be there, right? Here is the threaded portion, and this is the shank portion. It goes over here, and there is no threads inside this. No threads. We are not provided any threads in the hole. There is no tapped holes. Okay, so we are having threads on the externals. This is a nut. You can fix it on this one. So here you will not get any movement. This bolt, it is totally fixed into this, and you will not get any movement between the bolt and the hole. So that's why the stress which is going to occur here, it is called crushing, because bolt is a different material and flange is a different material. Flange is usually made up of cast iron, and the bolt is made up of mild steel, right? So using this one, so here we can get that one, that is the crushing stress. You will get two different parts will be there. It is joined and there is no relative movement. So that's why it is called a crushing failure. And the area, the area you will get it, this thing. So while designing that, I will tell you these things. So the other part which I have shown, the important one is this one. So this is called spine. There is a protrusion part in the left side part. So it is just like a portion, it will be like this. Some protrusion in the, okay. So this part, it is the protrusion part will be there, and this is the axis. Okay, this is an isometric. I'm drawing it so that you should understand this one. This is the flange. Okay. And here the projection part is there around 3 to 4 millimeter. This will be around 3 to 4 millimeter. And this is, if it is an unprotected type, so this will be a flange. Right. So this is the flange thickness, and here you will get the holes of that. If four pins are there, so in that case we can get this is a hub portion, right? So that will be there. So this part, it is going to fit it in this part. This is called a recess. Okay. So this spine, it comes in contact with this one. So when you fix these two things, so that means if I take one shaft over here and the other shaft is over here, so in that case I can say that they are in line with each other. So we can say that the alignment is proper. So this is a one type of check we are providing for the alignment, for alignment, because that is very important in rigid flange coupling, right? In the flexible coupling, so there is a flexibility we are providing it. Okay, so this thing it is we are taking in the rigid coupling. So again, once again, we will go for the thing that is here. I can show it. So rigid flange coupling, a flange coupling usually applies a coupling have two separate caster and flanges. Okay, each flange is mounted. Each flange is mounted uh, and keyed on it. One flange has a protected portion and the other flange is a corresponding recess. This helps to bring the shaft in line and maintain alignment. The two flanges are coupled together by means of bolt and nut. The flange coupling is adopted for heavy loads and hence it is used for on large shaftings. Okay, so this so types of flange coupling, and there are two types, unprotected type and then the protected type. In an unprotected type flange coupling, each shaft is keyed on to the boss of the flange with a countersunk key, and the flanges are coupled together by means of bolts. So in the protect, generally there are three or four or six bolts are generally it is used. So if it is less than 40, we used to take three. If it is in between 40 to 50, it is around four, and more than 50 or 60, it is six bolts we are considered. The keys are staggered at right angles along with the circumference of the shaft in order to divide the weakening effect caused by the key base. Okay, this is what I said it. The right angles, actually the left side shaft and the right side flange shaft, it is separated by at an angle of right angle. So this is provided in order to along with the circumference of the shaft in order to divide the weakening effect caused by the key base. Okay, so the protected type flange coupling. In a protected type flange coupling, the protruding bolts and nuts are protected by means of flanges on the two halves of the coupling in order to avoid danger to the workman. So this already explained with you with the actual diagram of the protected type and unprotected type flange coupling. So the other one is the marine type flange coupling. So actually in the marine type flange coupling, the flange is an integral part. Okay, the flange is an integral part of a shaft. So the end of the shaft is forged and they have made it in flanges and the holes, everything, whatever the things are there, and there's no keyway for the marine type flange coupling. So it is an integral part with the shaft. The flanges are held together by means of tapered headless bolt. The bolt head is not there, but it is a taper headless bolt. We are using it on the left side, and the numbering of 4 to 12, it depends upon the diameter of the shaft. So depending upon the diameter of the shaft, the number of bolts will increase or decrease, right? So now we will go for just design of rigid flange coupling. So that parts I have, this is the diameter of the shaft. Okay, this is the keyway in the left side, this is the keyway on the right side, and this is the spine, that is the protrusion part. It is also called as male plug, and this is female. So when it is matched here, we can say that is usually 95 to 100% alignment. We are going to get it. Okay, if D is the diameter, in that case the hub diameter will be twice of D, and this is called bolt circle diameter. Okay, or else it is called pitch circle diameter. It is 3 times D, and the outer diameter is 4 times the diameter of the shaft. So here the thickness of the flange is 0.5 D, and the thickness of the hub. So this portion, it is called hub portion, and this is called web or flange. This hub and web junction means this corner. Whatever you are seeing, this is called hub and web junction. Okay, so here when it is taken here, these are aligned. That means the alignment will be checked here. Okay, so because it is a rigid coupling, hence there must be some check for the alignment. And then we are inserting the bolt. Okay, this is the sectional view, total sectional view on for the left as well as right side. Okay, this is the, you can tighten this one. So you will not get any type of movement. There is no clearance, and the holes are reamed and grooved holes, and it is a finger tight. If it is a finger tight, then you can take n is equal to the total number of bolts n. As if it is 6, you can take n is equal to 6 for designing bolt. Or if it is a clearance fit is there, in that case, if there is a clearance between the hole of the flange as well as the bolt, in that case we can take it's equal to that some percentage. That means there is a torque, you will not get 100% torque transmission. So that's why we have taken half of that. That means it is just as good as you are multiplying the torque by a factor 2. That means you are designing the bolt for the higher load. Okay, so the design of flange coupling. So now we will go for the design of flange coupling. In that, first step is to find the diameter of the shaft. So even before the diameter of finding the diameter of the shaft, one must know what are the surface, permissible stresses for the shaft. So we can take there is a materials, or the one is the shaft, right? This is one. Okay, and the other one is you can have the flange. So it is made up of caster. Shaft is generally made up of a steel. Okay, flange is made up of caster, and again bolt, they are made up of steel or mild steel, whatever it may be. So that shaft and bolt and key is also, it is made up of steel. So 4 parts is there. One is the shaft. You already know how to design the shaft with the given stress. So the first initial step is to find the allowable stress. So here the flange coupling is transmitting torque. So hence we have to go for the tau s allowable. So tau s allowable is equal to 0.5 of SYT upon factor of safety. Okay, so this is for the shaft. And if it is for the flange, I will write as tau SF. It is taken as again 0.5 of SYT for the flange material and divided by factor of safety. Okay, if the flange is made up of say FG, that is gray cast iron of 200, and the factor of safety is say 5. Okay, if 5 is the factor of safety, so then we can have this one, that is what is the allowable shear stress for the cast iron. Suppose if you put it here, the flange allowable shear stress, it is 0.5 of 200. 200 is the ultimate strength actually, cast iron. So as it is a cast iron, so this whatever the figure it indicates, it is an ultimate. So zero point 0.5 of 200 divided by 5, that means 100 divided by 5. So that is you will get 20 Newton per mm square. So usually the value of gray cast iron, okay, the towers allowable permissible limit is towers is 20, and steel key bolt. So you are knowing already the stresses which you have already studied those things. So accordingly you can take now what is the crushing stress in the bolt, okay, crushing stress of the key, so like that. And now you say first step is to find the diameter of the shaft. So tau s is equal to allowable shear stress of the shaft. Then the design of the shaft is based on pivot torsion only. So we can have this equation, mt is equal to p into 60 upon 2 pi n. Whatever the things you will get, it is in Newton meter. Again multiplied by 10 raised to 3, you will get in Newton mm, right? And after this you can write down the based on the bending and torque. The equation for torsional shear stress is 16 into under root mb square plus mt square divided by pi d cube. As there is no bending moment here, we can write as tau max is equal to 16 mt upon pi d cube. 16 mt upon pi d cube. So r d cube is equal to 16 mt upon pi into tau s. From this I can find what is the diameter. So this is the initial step. We have to find the diameter of the shaft. So that itself indicates that it is the inner diameter of the flange, right? The hub diameter, if you take it, the inside diameter of the hub portion, it is nothing but there we are inserting a shaft. So that's why that is the diameter of the shaft. So as the keyway is there, so usually the 42, if it is a commercial shafting, in that case I can take tau s is equal to 42 Newton per mm square. Okay. And if as per the ASME code, if they are given, then in that case I had to use KT factor here, KT into MT. And then I had to, whatever the tau s value you are going to get with the ultimate and SYT, 18% of we have to take SUT at 30% of SYT, whichever is less value, and that should be multiplied again by 0.75. So that you will get the allowable shear stress. It is based on what? ASME code equation. So these are the things we have learnt already in the shaft design. So that thing you have to apply it. Okay. This is for the step 1. Okay. Is it clear to you? So now we will go for the step 2, that is the diameter of the flange hub. So this portion, it is known as hub portion. Here, this is the hub portion. This one, it is called the hub. So if dh is the diameter, it is 2d, and this is the bolt circle diameter, it is 3d, and d naught, that outside diameter, is 4d. So these proportions you try to remember it. And now this hub portion, we will treat it as a hollow shaft. Hub, we can design of hub is based on pure that is we are by taking as a hollow shaft. The outer diameter of the shaft is dh and inside diameter is d. So you just use the equation of hollow shaft, and then from that you can find what is dh. Or else you put the value of dh is equal to 2d there and k value, and put and find what is tau s, and that should come less than the tau s for the flange. So hub diameter of the flange is determined considering the hub as a hollow shaft, outside diameter is dh and inside diameter is d. Okay. So tau s F is the allowable stress. So then K is equal to, it is the ratio of inside diameter, that is the shaft diameter divided by dh. Okay. So this equation you are already, it is known to you. Tau s is equal to mt into c upon j, where c is equal to dh upon 2 and j is the polar momentum of inertia. It is twice of I, r, which is equal to pi by 32 into dh4 minus d raised to 4. By taking dh4 here, we can write it is pi dh4 by 32 into 1 minus k raised to 4. So putting these values over here, I can write it as for the flange. It is 16 mt upon pi th cube into 1 minus k raised to 4. So here you have to take that dh value. dh is equal to how much? It is 2d. And k is equal to d by dh, that is nothing but 0.5. And if I put that value, and you are knowing already mt, mt is how we can find p into 60 upon 2 pi n. So taking that value, and we can take that one and find what is tau sf, and this is the induced stress. It should come less than the allowable stress, or else using that value you can find dh. Okay. If it is coming more, you can have to find dh by considering tau s for the flange. Say if tau s for the flange is 20, so you just put the value of 20 and find dh from this. Okay. So this is the way to find out the hub diameter of the uh, flange coupling. So now after this we will go for the, so step 3, the design of flange thickness. So that is this thickness, that is Tf is equal to 0.5 d. So this can be designed as a shear failure at this hub and web junction. So this is the hub and this is the web. So at this part that may fail in shear. So that is here, if I show it. Okay. So here, so at this point, this is the, here you are going to get a failure in the flange. So if this part, the other part is stuck somewhere, and if this is connected to the motor and if it is still rotating, in that case you are going to get this failure. The flange part, it comes out as a ring, right? The failure at the hub and web junction. So that is the part of this. I can show it here. That is resisting strength in shear into dh upon 2. So resisting strength in shear, it can be calculated with the resisting area multiplied by shear stress. So mt is equal to pi dh is the circumferential length into the thickness, that is the thickness of the flange. If you do it, so into tau s for the flange, that is the resistance strength into dh upon 2, you will get the torque, right? So using this value here, I can use Tf is equal to 0.5 d and dh is equal to twice of d. So we can find what is tau s for the flange. This should come less than the allowable. Otherwise, take this tau s value as 20 or 15, whatever it is given, and then find a Tf based on that. So this is the ultimate. You have to find Tf or based on shear stress value, or else find the, you just substitute the proportional factors and find the induced stress, right? That should come less than the allowable stress. So here this is the area. As I said, if d is the dh is the diameter here, so if this is the thickness you are going to get, is that is a pi dh into the thickness tf is the area you will get. This is a, it will come out as a ring, right? So this resisting area is pi dh into tf. So the fourth step is the design of bolt diameter for the two things, that is see here, this is a flange it is connected by means of bolts will be there, right? These are left side flange is connected to the right side, and through the net we can fix it, right? So the torque is transmitted from the shaft to the through the key to the hub portion, and from the hub portion to the bolt, from this bolt to the other part. So like this is the path of the torque, right? So that will fail. There are two failures you are going to get it. One is a shear failure. It is suppose this part, the other part which is there where it is used, it is connected to a certain gearbox, let us say. So if that gearbox, if it is stuck or jammed, in that case, so this is in running condition. So ultimately, if a bolt is weaker, so in that case, you will get a shear failure of the bolt, right? If 4 bolts are there, 4 areas you will get it. If 6 bolts are there, 6 areas. So shear area in the bolt you will get. That the failure of the shear in the bolt. Or the other one is since the bolt is in contact with the flange. So as I said, the contact stresses will be down. So the contact, which is the contact length? So the contact length is TF, which is equal to 0.5 D. And what is the diameter? This is dB is the diameter. So dB into TF, it is nothing but the area of the contact stress, right? So like that, by using that area, I can find out what is the crushing failure. Okay, first we will go for the design of shear failure. So in that case, we can take n is equal to 3 for d is less than 40. And if it is 40 is in between, 40 is in between 40 to 100, it is taken as 4. Sometimes even 70, you can, so this is just a guidelines, you can use this one. So 40 to 100, if it is there, 4, and more than 100 to 180, it is 6. Okay. If dB is the diameter of the bolt, the resisting area in shear will be resisting area is equal to n into pi by 4 into dB square. If dB is the diameter, see here, this is the area you are going to get failure. Okay, so this area, it is pi by 4 into dB square. If tau s b is the allowable shear stress for the bolt material, so you should be very careful. So whenever we are using this equation, here the examiner will see that this is we have taken for the flange or the bolt. So if you are designing the bolt, you should take the shear stress for the bolt material. Okay, so it is usually it is around 40 or 40, 45, 50 Newton per mm square. So RLC SYT, if it is given on factor of safety it is given, you can take 0.5 of SYT upon factor of safety. Okay, and then dBc upon 2, that is the diameter divided by 2, that is the radius. So force into the radius. Okay, force into the radius, you will get the torque. So the applied torque is equal to n into the area, total area, multiplied by the stress is nothing but the resisting area in shear. Okay, resisting area or resisting strength in shear into tau SB into dBc upon 2. So number of bolts can be taken here, n is equal to n if it is a finger tight. If it is a clearance hole, and if the holes reamed and grooved holes, we can take it's equal to n is equal to n. It's a finger tight, we are saying it. And if there is a clearance, so in that case we can take n is equal to half. Instead of taking n is equal to n is equal to take it half, because if there is a clearance, so we are not transferring 100% torque. So that's why we have to n by 2, if you do it, that is as good as it is twice of mt. You are designing for not for the torque which is there, which you have calculated from P into 60 upon 2 pi n from the power. But you are multiplying that one by a factor 2, because you have made a provision of clearance. Are you getting it? So if there is a clearance, we have to take n is equal to n by 2. If there is no clearance, if it is not mentioned anything, you assume that the holes are finger tight, reamed and grooved holes and finger tight. Okay. So here you must get a very smooth surface. Okay. So this is about the design of the bolt based in shear. So now we will go for the design of bolt based in crushing. So as it said, so the crushing stress, where is that area you will get? This is the area, that is TF multiplied by dB. So here, this spot, this is the area you are going to get it. So this is the projected area. So projected area into the number of bolts. So that is the total resisting area in crushing. And if TF is the thickness and dB is the diameter of the bolt. So we are knowing already these things, you just put it here. Okay. So MT is equal to N into dB into TF into sigma CR into dBc upon 2. Okay. So here you just put the values, and after putting the values, you can find what is the thickness of the flange. If you are putting sigma CR is equal to, if you are taking the allowable stress, you can find TF, or else you just put the values, proportionate values. dB is equal to, you just calculate it, right? So that value I have to take it based on shear, and then TF is equal to 0.5D, you can take it here and find the sigma CR, and this should come less than the permissible stress for the bolt material. If the induced stress is coming more than the permissible, so then find out dB based on crushing. TF, you don't find it, TF you can use it as it is, you can find dB. Okay, so you just put the value of sigma CR. Let us say for a steel, it will be around 70 or 80. So you can put that value here and find the dB based on that. Okay. So these are the things you have to do it. So this is based off a bolt based on shear and crushing. So the next one is the last part is the key. That is the design of key based on shear and crushing. So if F is the tangential force acting on this, right? This is the hub portion where the shaft is there and we are inserting the key, right? If L is the sun key, L is the length, B is the width, T is the thickness. Okay. So in that case, F is the tangential force acting on this, right? So here the area you can see here, this is you are going to get a failure. Half portion will be retained in the shaft and half portion will be retained in the hub in direct shear. So here L is equal to 1.5D, you can take, B is equal to D by 4. By taking that, we can find MT based on this shear. So here, so this is how we are going to get a failure in the shear. Okay, so that is the area. So as it is shown here, so this area, this is retaining in the shaft and this part is retained in the hub portion. Okay, so B into L into tau S for the key. You just put the values here, find tau S. That should come less than the allowable. And if it is not coming, you just find B from this. Okay, L is equal to 1.5D, as it is you take it. Find B based on tau S value. Tau S for the key. Okay. So similarly, design of key based on crushing. So as you know that crushing failure, it is again force, it is subjected here. So this force, so this will be in contact. So the part which I have shown here, so this point, this is the surface, it is in contact. So here, this area, this will be the engine contact. So this length will be L and the thickness will be T by 2. T by 2 into L is the resisting area in crushing, and B is equal to D by 4, T is equal to D by 6. Taking that value, you can find MT, that is a sigma shear you can find out, and that should come less than the allowable crushing. If it is coming less than allowable, it's okay. Otherwise, find T based on crushing. Okay, you put the value of crushing 70 or 80 and find the thickness. Okay, so this is the design of key based on crushing. So the other part which is there for the flanges and all, that here as I shown here, this one, so this diameter, so d naught, which is equal to 4 times d, since already we have checked for dh, it is checked for the torsional shear stress. So since this diameter dbc or d naught is equal to 4 times d is more than dh, so then the allowable shear stress value will come definitely less than that. So that's why no need of shear failure, we can check it for this one. So we can take that as a proportions. So these are the things, and protected type flange coupling, you can just take the proportions. There is no need of designing the what is the protection part of that one. Okay, and finally the conclusion part, you can say in the we enhance the life of the machine component. Discussions are made on the design of rigid flange coupling. Since it is not possible to have a perfect alignment two joining shaft, this coupling is used for the medium speed rotating shaft transmitting at high torque. So this is about the rigid flange coupling.